Oni zapały, Louis Samuel Chiwaju Bijedu, Genil Skidgen, Genug, Duinagan Zigol, Chquabonak. Donke, Milos Wellman Kinzazug, Mavik Jima, Jibet Wazik. Some background is relevant. In the old stories, glaciers were alive. They stormed across the plains, brought fire and judgment on human beings, or they led the good-hearted hunters to find their animal relatives, or they wandered in the form of mist and drifts of snow, searching for certain kinds of love. This is a collection of graphs. I know it's way too small to make out any single thing. Don't try to look at it too closely. But it is graphs of glacier disappearance over different regions and climate projections. The important thing to note is that all the curves rise and then fall, and they fall because you cannot lose something once you don't have it anymore. Over here, we have pictured some ways that these departing glaciers affect us. Rock slides, floods, some can cause tsunamis if enough land falls into the water. And we are trying to understand these, but there is a challenge because no geophysical signals manifest across all landslides and landscape movements. With this work, we are going to ask a slightly different question, inspired by one of the scientists I admire who encourages us to look, I should be pointing with my mouse also, to look in terms of energy, frequency, and vibration, which I interpret as the change in things, to look beyond the static and the structure to the process and the behavior. We are going to ask if a graph neural network, so an instance of a machine intelligence, can read and interpret the signals of a glacier, the ghost of a departed glacier, the ghost of a landscape, if you will. And this matters to us in a very practical sense because it affects our infrastructure, our connections through roads. It affects the places where people live and the way we interact with the landscape. And the work in general gives a framework that can be built on, we'll talk about this later, to incorporate many more forms of data to ask many more questions about landscapes. This is what we'll do. We will manipulate some DEMs. We will use their outputs to build theoretical graph structures. I will ask you to please suspend for the next 10 minutes any previous concepts of what a graph is. And then we will train a neural network with those with that graph structure. We're working with Animal Glacier because we have been there and we have data for it. These are pictures from our visit there last summer. We were looking for permafrost. We did install one thermistor. And we also collected some TRI data of slopes that I wasn't sure exactly which one it was, but they look kind of like this. And you see this visible scarping. And this is, by the way, maybe not that one, but this is the back end of the slope that we will be looking at in the DEM. Just for comparison, there are some clear differences in climate between the Juneau, well, yes, the Juneau Icefield and the Canmore Glacier Valley, but they are both this sort of moderate elevation, and they have some ice, and as we just heard, that ice is changing. So this is, oh, we work with two data products. This is one of them. It is a very high resolution, 1 meter LiDAR digital elevation model flown by Chris Larson. And we took that and we people can see this. So we isolated this north slope and we isolated the basin. So for this one, the north slope is what matters because we took that north slope, we took the 1 meter resolution DEM, derived the slope and the aspect. And then this isn't quite curvature. I called it double slope because it's just the, GDAL, the slope of the slope, which mathematically is kind of curvature, but and it just gives another signal for the machine to process. This is our second piece, also processed by Chris Larson. And what Chris did is he took that 1 meter DEM that was flown in 2025 and made a difference DEM between an IPSAR DEM that was from 2000. So what that gives us is a 25-year difference in this valley and this basin. And we took that and isolated that difference again to that same north slope area that we did for the four features that we saw in the previous slide. And we also isolated the glacier basin itself. And I will say basin, 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 because that is going to be a very important piece later. So we have these two separate pieces. So now if you remember, we have 4 features on the north slope. We also have the difference for the slope, and now we also have the difference for the glacier basin. Now when we're, this is sometimes a, maybe not conflict, but a confluence between natural science and applied mathematics is sometimes you don't know your science question. Maybe this happens normally. You don't know your science question until you've just sort of played with the data and seen what the data can show you. And what we have here is, these were two of the things that sort of stood out while we were processing the data. This is that difference DEM pasted alongside the basin, and this is the slope. And please forgive me, this happens a few times in the slide. This is the exact same slope data as before, and I think the color scheme has changed. But we do this because at different color schemes and maybe even different ranges, it highlights different aspects of the property. Aspect is also a feature. We're also using feature. Different underlying signals of the property, right? And you can see here that closer up to where there is less change, right? So this is very intense change. Where there is less change, you see that the steeper slopes are still higher up on the slope, if you will. Whereas where the change has been more intense, the steepness has sort of fallen. And you can sort of see that here in the difference. Now, dark blue and dark red brown are both high difference. It's just whether the difference is positive or negative. So you see here that there is differencing, or the differencing is more intense. The differencing is arranged differently higher up where the glacier is still more stable and has these sort of inverse differentiation where there is more glacier retreat. This is where we talk about what a graph is. So in graph theory, a graph is a collection of nodes and the edges that connect them. There are many ways to connect the nodes and their edges, and there are many ways to arrange nodes. In some cases, you will see that maybe each of these mountains would be a single node, and we would connect them by sediment connectivity indices. In this case, we assigned every 3-meter grid square one node, and we set edges basically sort of intuitively, meaning their nearest neighbors. They're precisely nearest neighbors. So they're cardinal neighbors, north, south, east, west, and they're diagonal neighbors. And there's no great way to visualize a graph that has 4 million nodes on the space. So what I've done here is make this blue sort of fuzz over where the graph covers. And then you can imagine that it looks like this, but extrapolated out to this entire area. Every single node had these 4 features. And then they also had what in machine learning we call a label, which is something that you train on, and we'll talk about that in a second. I think that's everything for the graph. So now graph neural networks do something a little bit different from the standard array of conventional neural networks who tend to work off matrices and grid data, and however large your input grid is, your neural network is sort of required, unless you do some weird manipulations, is required to look at that whole input and draw conclusions for whatever target output you're looking at. What a graph neural network does that is a little bit different is that it starts aggregating information from the node in question to progressively larger radii of neighbor nodes, and at each stage draws conclusions from that information. And I should probably say just a quick overview of how machine learning works. So in this case, we're doing what is called a supervised training. So we have the features, which are the elevation, slope, aspect, double slope, and we have the label, which is the difference at each node. On the north slope, which we talked about, the sum of those nodes will be covered up, or some of those nodes, their difference values will be covered up. So the neural network is allowed to see the features of that node and the features plus the difference of other nodes, and learns to predict what that node's features will be, that node's difference will be based on that node's features. And I was going to do this in 2 slides to sort of save the surprise, but these are our results. And the thing to note here is that, so this is our true unmodified prediction. This is where I said the colors will change. This is still the difference DEM on that north slope. And this is the difference DEM predicted by, I forgot to say this, we did a 70-30 training test split. So 30% of the north slope nodes had their difference values covered up during the machine learning training. Now, so this is the model's best prediction on that north slope difference when it was able to train while also looking at the signal at the difference given by the basin. And this is its prediction when it trained and was not able to look at the basin signal. And this is the residual, which is the, if you take this, the true difference minus the predicted difference, you get this residual where white means you're closer to the stats where I had them on a previous version of the slide. The mean was near 0, but the standard deviation of this one, and you can see it here, is a lot higher, where red and blue are both higher extremes of not being close to that mean. And what that tells us is that it looks like a graph neural network can learn the change around the basin. Oh, and learn the change around the basin from the basin change. Now, it is worth noting that we only use those 4 features from the LiDAR DEM, and we'll talk about what that implies later. There are other things we can talk about, physics informed, that are a little bit beyond the scope of this particular project. Now, this 25-year difference DEM is also a huge span of time to be getting glacier retreat. I mean, we can see, what is the scale that we can see retreat differences? Someone who knows. In a year? Yeah. We can see differences after a year, right? So 25 years is a lot of compiled change. We still learned something. We'll talk about what that implies in a second. The random sparsity is something that can be improved. And one of the things we can do is to sort of make patches of nodes whose differences get covered up. And so now the network has to learn patches or even entire landforms. So what can we do? Well, there's a lot of ice on Juno. It is changing, as we just learned. There are valleys around it. There are nunataks whose scree is held up by ice. That ice is changing. So there's a lot of room to investigate learning this ice change signal and correlating it to landscape change. Also, remember, we talked about those 4 features that were all derived from one LiDAR product. What if we were able to incorporate that TRI data? What if we could include radar layerings, human observations, UAV observations, borehole ground truths, all the things we talked about in this conference so far, as well as once we start monitoring things on these annual and seasonal scales, if we can learn to associate some of these things with the differences at those scales, well, now we can go back and say, we've been collecting radar data for years. So now we can learn more things from that radar data, now having it correlated to these other modern investigations. And we can potentially go forward in time by making predictions by using change simulations based on climate scenarios. These are some of the references I used. And if we go back to the quote that originally inspired us about the energy, frequency, and vibration, we might also think that can now add graphs to it.
You did an amazing job, and I was trying to keep up. Could you just go back to the basin, no basin, where you showed the results?
This is very cool.
Yeah. Well, no, my very basic question is, just explain to me one more time what the basin, no basin thing is. Because yes, I agree, it's very cool. I just want to make sure I'm on the.
Yeah, no, he just showed me yesterday, and I
think
think
the other
it's the
one.
next
Yeah,
week.
it is. I think this will help though, because so this is the entire difference DEM, or for the entire region that we chose.
Yeah.
And what happens is the graph was built over. I actually misled you guys because the graph was not only built over this, it was built over this entire region. So this whole thing should have been light blue. And over this entire region, every node had its features, its 4 features. But then when we did the training, we first trained the model. So on the first iteration, 30% of these different nodes were covered, and the model learned to predict their differencing. In the second iteration, we hid all of these different signals. So the model was not able to read any of these different signals. The nodes still had their features. And it was only able to look at 70% of the differences here, and then learn to predict the other 30%. And so between those two models, that is where the one that was able to look at, this is the one that was able to look at the basin signal, and it recreates the rest of the slopes difference with some better granularity and almost intensity. The standard deviation is a little wider, which you want here because you want it to incorporate more variation, more almost to have it be a little bolder in guessing what the changes are. Whereas this one is a little more, everything is closer to the average. And did I answer the question?
Yeah, no, keep it up, thank you. Good.
And then this one here, you see that this is the residual. So this minus that, which you want to be as close as possible to 0, which this is in more places than it is here. You see more intense blues and reds here because the difference between the prediction and the true has greater predictability.
Awesome, thank you.
I have a couple things, Nestor. So I think one of the things that came out when he was showing me this yesterday, that at least in my mind, is that if we want to go predict the landscape change in a currently glaciated area, then we need to know, or we will be better served if we predict first what the ice is going to do in that area, which is not really a surprise, but this is really showing it quantitatively. So you could go to Alps or Juneau Icefield or wherever you want, and you want to know, okay, how stable is the land surface that, even if it's not currently covered by ice now, will be. But you're going to get a lot more accuracy if first you figure out what the ice level is going to do, and then use that information to help predict what the slopes are going to do.
So, can I ask a question real quick? I mean, like, I'm thinking about the talks that we had yesterday as well. Billy gave a great kind of overall summary of what their team's doing to determine some Gilkey Glacier, and where the team's working at the upper reaches of the Gilkey Glacier and more in the accumulation zone. Well, I guess we're still in the accumulation zone, but we're higher on the glacier. So I kind of wonder about, they're diving into glacier change modeling, right? And that was a part of the discussion yesterday. But this is, to me, a good example of a take home for, I'd like to hear your thoughts on it, but a good example of take home of where we can merge forces to get more bang for our buck with another team working on a different part of the problem that will contribute to the type of work you're doing. Is that kind of what you might have picked up yesterday? That's kind of my question for you, I guess, if you saw Billy's talk. I don't know if you saw Billy's talk or not.
Was it in the morning?
That was afternoon. So Billy talked about basically the Gilkey Glacier, and they're doing terminus work, looking at the glacier change at the terminus and the lake terminating glacier. And they're doing a bunch of GPS observations, kind of lake observations, maps, ice thicknesses, and they're modeling the glacier change of Gilkey Glacier. And I know they're keen on our off glacier observations. They're mostly working at the terminus, but they are some involved the overall elevation of the glacier. So I guess that probably gives you enough information to think about that site for this coming summer even.
Yeah, I think so, absolutely. And one of the big lessons that I learned from going through this was how important it was to work closely with the people who are collecting, or in this case, like creating You know, the output of a model can be data for another model. And so to work closely with and really understand what you're working with. So yes, absolutely. And the more, you know, I have all these things here, and the more, you know, my limitation right now in using these things is that in many ways, I don't exactly understand them or what the readings are and what they're doing. And that's part of why I'm in Seth's and Renee's geophysics class. But the more, you know, the more we can understand how all these pieces can fit together and what the different signals can be hoped to tell us, the more, you know, we can have radar readings over here, borehole confirmations over here, UAV observations over here, TR on some slope over here. And all of these things can be propagated by that aggregation over the grid, and give us meaningful insights. That's the goal.
Another lesson is regular high resolution LiDAR will benefit a lot of people. Even if you don't know how you're gonna use it. I mean, cause like that 2000 data set is, you know, irreplaceable, obviously, so super important.
Oh, please.
Okay. I was wondering, can you go back to the last slide? And like the difference through. I'm wondering if you can back out. Okay, so two-part question. Can you back out process from the graph network? Like, why does it need the glacier? Somehow look at, I know these things are black boxes to a degree, but like, why does it need the glacier specifically to predict? And sort of building on that, like the residual plots, like it looks like it does a lot better. Like if you right at the edge of the glacier, like why is it specifically able to learn something like right there? Yeah.
Those are two very interesting insights. And one is, yes, they are black boxes. There are ways to sort of tease some extra insights out of them. You know, we didn't have time for this, but we could do like feature ablation and sort of remove, you know, we did 4 features here. We could say, well, what if we didn't show you the slope? You know, could you still, you know, what would your results be? What if we didn't show you aspect? And so we could see, you know, what is driving it. We could perturb some of those values. So we could get some insights there. As far as these, something interesting to note here is that a lot of the change along the edge is actually a piling up of things that have accumulated. So I have a guess that I just made up. So I'm gonna share it with you. But yeah, you know, so the when you're starting to talk about these edge pileups, you are now talking about something that is sort of an accumulation of multiple behaviors. Whereas, oh, did something slip from here might be something that you can more easily predict. You know, whereas you have this accumulation here. And so again, going back to whatever it is reading from that basin signal, it might be giving it the machine intelligence more context to be able to explain that process with more nuance.
Well, I think another way of saying what you just said, Nestor, is that in the lower model, or the lower model doesn't know that there's accommodation space because the ice surface is lower.
Mm-hmm.
Is that a fair?
Doesn't know that they're.
You said it again, Chris?
It doesn't know that the ice has dropped, so it doesn't know that there's now empty space that can be filled.
Peter has on his end.
Interesting.
Yeah, right. I think the accommodation is sensible, but I think much more sensible or additional is the driving forces change hugely as a function of that fall, and that's defined by the position of the basin, which is really indicated by this work, Nestor. I think it's really good, and I like having that you split it up into these with the basin, without the basin. But again, it leads to a distinction of what the physics informed component will be able to add to this, at least be able to be checked. So I think it's nicely laid out, and the fact that it does change in the way that it shows here between the basin used and the basin not used is really useful too, and for prediction of then extending this generally to glaciated, deglaciating terrains around the world.
Yes.
Yes, really interesting stuff. I was wondering if there's any way you can use those ground truthing and other different types of data that have different spatial resolutions to the LiDAR in the model training, or is that something you would use just to compare the results to after you've predicted differences?
First of all, absolutely, you can. It kind of depends. And when you say ground truthing,
Just any other different types of data that don't have the same resolution as the LiDAR. So if you've got like 5-point measurements across your whole area, can
Right.
that be?
absolutely,
Okay.
absolutely. And the way I see that is, what are we doing on time? Are we over?
You got a couple minutes.
And this, I think, is especially valuable once we start adding other forms of data, because if you have some radar over here and some ground truth, well, ideally they overlap, then you can learn something from both the ground truthing and the radar, and then in all the places where you have the radar, those are now more validated, more verified. And then maybe radar overlaps with something else or is near something like TRI, and then that going a little bit beyond what I can confidently say from the mathematics and the machine learning that I understand so far. So I think I will stop there. But there are one of my favorite papers about graph neural networks does precisely that. They do a sort of spatial interpolation of temperature using boreholes that are, there might be one here, one here, one here, one here, and multiple other forms of geophysical data, like gravity, like radioactivity, like proximity to faults. So it's all scattered, it's all over the place, it's all inhomogeneous, and the signals, the graph neural network was able to transport those signals over the graph.
All right, one last question from Kaya, then we need to move on.
Cool. This is a philosophy question, if that's okay, and also probably reflects the fact that I teach at a liberal arts school. I love that you started with us thinking about kind of the like traditional ecological knowledge of this place and the like storytelling of people who live in these places that have experienced glacier change. And then we went in this direction of using computer intelligence, neural networks to understand change that's like beyond the human brain's ability to like put data points together. And in some ways, I feel like those like schools of knowledge almost feel like antithetical to each other. Like one is a very like lived experience, and the other is a very like beyond what humans can perceive experience. And like, yeah, I'm just interested in your perspective on like what can we draw from both of those like schools of thinking? Are they actually antithetical to each other? And how do we, in the pursuit of more knowledge of this system, how do we like pull from those different schools of thinking in a cohesive way?
I have no words for how much I love that question. So in the 1980 classic Waves and Beaches, Willard Bascom, an oceanographer, distinguishes the difference between a scientific tool and a scientific instrument. Tool, according to Bascom, is something like a camera that is augmenting one of our senses, whereas an instrument is something that is actually reading something for us that we cannot perceive. So, and that would be something like radar. So, a machine intelligence is, in that sense, is an instrument. And the thing that it is detecting for us is, in a way, probability distributions. That is the mathematical version of it. But if we go back to the storytelling and the sort of perceptions, you know, the way we live now in the Western world is not always how we and our ancestors were. There was a time that we were connected to the land and that we saw the spirits in the things. And so that, to me, is just, it goes back to, you know, what we think now are things that are spirits and these abstract intangible things might very well be there. Again, I'm getting a little bit outside science, but I'll just say that it is not shocking to me that a machine intelligence is finding ways to read signals from this ghost of a landscape to things that we don't typically think of as having intelligence, but you know, it's one universe and we're all part of it.
But also, and this is just sort of parroting what you've told me, is that we have the ability through fuzzy logic to actually incorporate those stories into the machine learning and bridge that sort of oral history and machine intelligence gap.
That is the goal.
Yeah.
What did I do?
No, thank you for sharing. I think it's a really interesting space to think within.
Thanks, Nestor.
Thank you. Oh.